Hey everyone, welcome back to MLWorks. In this video, we'll learn how to write a Cuda program for layer normalization in neural network. Specifically, layer normalization is used in our transformer architecture. So layer normalization is a technique that will help you to normalize the inputs, which in this case is features of your sample. And it is basically used for stabilizing the training process such that you can converge faster and speed up the speed of your training process, and also avoid vanishing gradient or exploding gradient while you are training. So consider you have three samples and you have four features. So what you do is basically you find the mean and standard deviation across each sample and use those values to normalize your input such that all your inputs will be consistent. So when it comes to Cuda programming here, so what we do is consider you have three samples here. 1, 2, 3 is one sample, 3, 3, 3 is another sample, and likewise. And there are three features, which is C1, C2, C3. So what we do is when you're trying to run or take these samples into your Cuda memory, what you do is you turn them into row major order as shown here, like 1, 2, 3 followed by 3, 3, 3. It will be allocated in a continuous memory block. Okay, so for this you have to ensure the specific element, right, which is R1, C1, R1, C2. These elements have their index appropriately assigned. So we have this specific formula for that, by which we'll be getting 0, 1, 2, 3, 4, 5, 6, 7, 8. So where R represents the index of the row, C represents the index of the column, and N represents the total number of columns. So this will result in 0 to N is your index for this specific 3x3 matrix. And what will happen when you are trying to run this code in Cuda kernel? So this will fetch each row, and each row will be running by a specific thread. So if you have 10 cross 10 matrices, there will be 10 threads, which is taking care of all your 10 rows of your matrices. So in this case, you have 3 rows, so you will have 3 threads inside a block that will be taking care of your operations. So now let us walk through a simple example for layer normalization. So consider you have a matrix 3 cross 3. First row is 1, 2, 3, then second row is 10, 11, 12, and third row is 0, 0.5, and 1. So what you do is, for the first row you find the mean, for the second row you find the mean, and third row you find the mean, and then you calculate the standard deviation for each. So if you see here, so for first row, this is the mean, this is the variance. Once you calculate the standard deviation, you will normalize it and you will get a set of values, which is your normalized value for this specific input. Now similarly, for row 2, you will have some output after normalization, and for row 3 you will have a value after normalization. So what basically happens is, whenever you are sending an input A with different feature values, after normalization they become consistent and have a uniform distribution within each row. So this is what we want to achieve with the layer normalization. So with that understanding, now let's go ahead and implement this layer normalization in Cuda program. So let us start by creating a file in day file, which is layer normalization, and which is a Cuda file. Now under this, first we'll start with the header imports. So what we do is, first we include IO stream, and then for math operations we'll include CMath, and then for some Cuda runtime operations we include Cuda underscore runtime dot h. So next what we'll do is we'll create the kernel function, which will take the input array A, and we want to perform normalization and store the results in array B, and we also want to take in the number of inputs, which is number of rows and columns. So it will be starting with global qualifier, return type of the function, and layer norm, and here we'll take the array float it is a pointer variable, and then float, again a pointer variable b, and then int rows, int columns. Now we have declared the function. Now let us start creating the thread index, which is a global index which will represents the row of your matrix. So int row is equal to block id x.x into block dim.x plus thread index, which is the index of the current thread in a block. Now let us do the boundary check where row is less than rows, because we don't want to access an element which is outside of the matrix boundary. So with this boundary check we will perform that, and now what we have to do is we have to create a shared location, which is done with the help of extern underscore shared, and then return the return type or the data type is float, and this is shared variable name. Now we want to have a pointer to this specific shared memory location. So what we do is we create a pointer variable row underscore data is equal to shared semicolon. Now what we have to do is this will contain our data, so we want to move this data to the shared memory location. So for that what we have to do is first we iterate through integer columns is equal to thread index dot y semicolon calls less than columns semicolon, then calls plus is equal to block dim dot y. So this is the thread index, this is the other coordinate of your thread. So if you go back to previous video, right, where I talked about the thread containing different coordinates like 0, 0, it also has 3 coordinates x, y and z, and by default some values are present. If you are not mentioning, there will be certain default values are present. So here what we'll do is we'll be having thread index getting generated here, and there will be some default value set here which is 0 initially. So we'll be incrementing by block dim.y. So when we are calling the kernel function, we'll be sending block dim.x as 256, and the default value for block dim.y will be 1. So it will be incrementing the thread index by 1. So let me update now the shared memory location, which is row underscore data, and here what we want to do is we want to update the columns is equal to our input is stored in A, so take the values from there into calls plus column. Yeah, so we'll be filling our row data like this. It will be 0, 1, 2, 3, 4, 5, 6, 7, 8. If it is a not 8, if it is a 10 cross 10, it will be 0 to 9 values that will be present here. So once we have our data stored in row data, what we have to do is next we have to calculate the mean. So float mean is equal to 0.0f semicolon for. Now we have to iterate through this shared location and calculate our mean for that specific row. So just to go back a little bit. So whenever we make a call to the kernel function, there will be multiple threads getting generated. So what will happen is when you make a kernel call, so there will be multiple threads generated like mentioned here 0, 1, 2. Since it is 3 rows, so there are 3 threads will be generated. In our case, if we have 10 cross 10 matrices, there will be 10 threads that will be generated, and that will be accessing all the 10 different rows that is present inside your matrices. So here currently we are handling our first row, assuming we have working with the first thread. So columns call is equal to 0 and call less than total columns semicolon calls plus plus. Now what we have to do is now we have to calculate the mean value. So mean plus is equal to row data and then call. That's it. Now once this is done, we have to perform division with calls, total number of columns, and that's it. We are done with mean. Now we have to do the same with variance also. Only thing is the formula will change. So for variance, first initialize the variable variance as 0.0. This is that. Now here comes the difference. Updating the variance here. So here we have to minus with the mean value, row underscore data for column minus mean. So we have calculated the variance. Now not variance, so here we will be calculating the variance. Now what we have to do is we have to calculate the standard deviation. Or before we do that, let me just update this one right here itself. Float standard deviation is equal to square root f of variance plus 1e minus 7. Why we add this is because when you are dividing with the standard deviation, if 0 is present, we don't want to throw in 0 error, divide by 0 error. So that's why we add a small value here. Now let us normalize. So what we do here is, again, first let me copy this. This is the block we need. So for end thread x, and here instead of row data you will have b, and here we'll have row into calls plus column, and here we'll have our what is the shared memory location, row underscore data column minus mean divided by standard deviation semicolon. I'll just add this here. So I think we are done with the specific aspect for int column thread index dot y. Columns. So this is done. So now we are normalize the value in the kernel function. Now what we do is we want to call this kernel function. That will be done in the main function. So int, let us define the main function. So here first int rows is equal to 10 semicolon, int columns is equal to 10 semicolon, and there will be float which will be a and b, and we'll provide some memory to these variables, which will be done with the help of malloc variable, malloc keyword. And here we have rows into columns into size of which is float, and then we have to do the same for b. Now this is done for when we are trying to initialize the program. Okay, our data will be stored in CPU, so these will be stored in CPU, A and B. Now we want to create variables which will be stored in GPU. So what we do is first we'll declare float star d underscore a and star d underscore b. Then what we do is we'll be allocating the memory as done here for this a and b. So here it will be Cuda malloc followed by the pointer or address of DA and rows into columns into size of float semicolon. So similarly we have to do it for DB. Now we have our memory allocated for the device variable, which is DA and DB. Now what we have to do is we have to move our, first we have to send some data into A. Okay, so what we'll do here is, let me iterate through all the indices here. Int I is equal to 0 semicolon, I less than rows semicolon I plus plus, then comes for int j is equal to semicolon j is less than columns j plus plus. Now a is equal to for this I into number of columns plus, and we'll be taking the column which is j value here. So what we are trying to do is we are trying to store the matrices in the row major order, if you know what it means. So this is the row major order. This is the matrix 2D format. We turn it into row major order by using these indices. So that's what we are doing here. So here what we can do is first we can take probably some float and a random input rand max. So yeah, so this will generate some random values for the A matrices. Now then we have to move this data to our GPU memory, which is DA. So what we do is Cuda mem copy, and here will be from first is the destination address, which is DA, and then the host address, which is A, and then comes the amount of data you want to send, which is rows into columns into size of float. And then what we do here is Cuda mem copy, and we want to send data from host to device. So this is done. Now let us define the kernel function. So here configuration should be updated into block size is equal to 256, int grid size is equal to, the formula is n by block size, that is rows into plus block size minus 1 divided by block size. So this will give us the grid size, which will be an integer. Now we have to make a call to the kernel function, which is LayerNorm, and it will take in first the grid size, then the block size, then the amount of memory that needs to be allocated for shared memory, which is equal to rows, which is equal to, I think we are going to send around list of like the whole matrices, so it will be rows into columns into float, size of float. So this will be the memory that you want to give for shared memory location, and then we want to pass our device variables DA, DB, and then rows, and then columns, semicolon. Now what will happen is once this call is made, there will be if you are sending 10 rows and 10 columns, so 10 threads will be generated, and each thread will be going through this function call, and it will be calculating the normalized value for each row. So once that is done, it will be storing the results in the DB variable. Once that is done, then we want to move back from device memory to CPU memory. So I'll be passing here B, and here I'll be taking from DB. So this is, instead of host to device, it will be device to host, and that's it. We want to free the memory which is allocated for these variables, which is DA, semicolon, and then so what we'll do is first DB, then what we do is for this array that we have in CPU also we want to free them, which will be B, and then we have to return 0. Integer is the return type, so we keep it as 0. Now we did not print any results till yet, so let me just print the values here. So first I'll be iterating through the matrix A, which is int I is equal to 0, I less than, probably it will be columns, right? It's rows, semicolon, I plus plus, then for int j is equal to 0, j less than columns j plus plus. Then we have to do standard cout. It will be I guess percentage f2 percentage 2f, and I'll be taking the a is equal to I into columns plus j, and then I'll be adding some space here between the elements, and then here. So I think something is going wrong here somewhere. Maybe I have to keep it like this. So let me just keep it here, let's keep it like this. Now let me add a new line here. So this is done for A matrices. Now let me do it for this one. This is for B, which contains our result, normalized values. So normalized values will be same as the for each row. Now here I have to print the semicolon. We are done, I guess. Now what I'll do is I'll be just moving to this folder, which is day 5. I'll call the compiler nvcc, and the file name is Layer Normalization. Output is stored in LayerNorm. So let us see. So it will automatically generate 10 rows, and then it will be printing the normalized value for that specific 10 rows, and the results will be having same rows because it should be consistent. So let me see the output here, LayerNorm. So we are seeing a consistent value that is coming here, and this is the random values that we are generating. So these are for these first row, this is the normalized value. Similarly for second row, this is the normalized value. So it is the same. So at the end of the day, what we want is, if you see here in the sample walkthrough, what we have done for different set of input values or the feature values that you have, once normalization is done, we'll get our uniform distribution within each row. So that we have seen here. So with that, I'll be concluding this video. Thank you for watching. And if you are trying to learn Cuda program, then you should follow this series where I'm teaching all the basics of Cuda GPU, how to move data from CPU to GPU, how to allocate memory in shared location, and how to utilize the threads effectively to perform parallelization. So we'll see you in the next video. Thank you.